Okay, so what I do, I handed out the that test review. Okay, so our test is Monday, right? There we go. So we got Hooke's Law. That's where we started. So we're going to start at the last midterm and kind of go from there. That's what we're going to do. So we're going to do Hooke's Law, which just converts from 2D stress to strain and from strain back to stress. We skipped these. We're kind of getting a little behind, so I decided to take those out. So they're gone, okay? Don't need to be worrying about those. And then we did plane strain, which is that biaxial strain stuff. So deformations, strains on given elements and planes, which is at epsilon x1, gamma x1, y1, and alpha. And that could be sketching, okay? What's that? We're good?
The principal strains is already off of ours.
Oh, it is it? Okay, yeah, all right, thanks. Okay, and sketching. And that's, there were three varieties of that. There were the schematics where you dimensioned everything. There was, we did some rectangles where we used the lower left-hand corner as the reference point. And then I had to do a circle where you used the middle as a reference point, okay? So those are the different kinds of sketches that we did. And we did pressure vessels, hoop and axial stress. Hoop and axial stress and principal stresses. Remember, the hoop and axial are the principal stresses, right? And then in-plane stresses and strains. So that's the biaxial stuff is what I mean by that. All right. And so, I don't know, it's just a matter of vocabulary here, but this, when I say plane strain there, I mean biaxial. What I mean. Got a little trouble with my pen here. So that's biaxial. And then we've got, when I say, again, in plane, that means biaxial is what it means. So you had that one problem, that one, I think it was 253, I think, for the pressure vessel where you found the hoop and axial. From there you found the stresses at angles. You found the stress on two planes. And then you found the lengthening of a line. Is that 253? I think it is.
That's about the welds.
Yeah. That's basic. That is 253. Okay. All right. And then we're doing the stuff now, which is torsion. Okay, shear and twist angle, which is phi. Right? Or no, shear is tau, of course. Twist angle is phi. Non-uniform torsion, in-plane stresses and strains, and then power transmission, and then we're about to do indeterminate torsion. Okay. And then I gave you some example problems there. So what do we got there? Find the shear stress and the angle of twist. So that's just the basic formulas there in I. That's indeterminate. That's kind of a indeterminate torsion problem there, more or less. And then here's one of those pressure vessel, find the stress on a plane kind of things. If you want to find the stress, what angle are you going to use for that one?
20 plus 25.
20 plus 90. Yeah, 110. Yeah, okay.
I was thinking of strain.
Yeah, I know. That's why I'm bringing it up, because there's so many of these different relationships. So when you're doing stress, what you do, you reference to the vertical plane, right? So that's what you do when you're doing stress. And I didn't draw that quite vertical, but you get the idea. So that'd be
110.
Yeah.
70 would 70 work? Or?
No, well, negative 70 would work, but it would have to be negative 70, because 70 is clockwise. And by convention, that's negative, okay? So you could use positive 110 or negative 70.
Right.
Either one.
What you would initially assume.
Yeah, okay. And see, the reason for that is if you double them, if you double 110, you get 220. because what you put in the formulas are 2 times, right? So if you double 110, you get 220. If you double -70, you get -140. -140 and 220 are the same angle. See, they're both the same angle. Okay. All right, so just remember that, okay? Okay, then what we got to do here? We got to find how much longer line AB would get. So you got to find the strains. Now notice on this one, I didn't give you the signs on the strains. You got to figure them out. I just dimensioned it. So you got to figure out the signs on the strains. And then you got to run the equation and then figure out the new length of the line, okay? So that's got a few little steps in it, that one. Oh, this one's kind of funny. This one, some of the stuff, you know, it takes so much time to do it. Sometimes I just asked, like, okay, here's a thing I want you to do. How would you do it? What formulas would you use? What would you put into the formulas? And what would you get out of the formulas, okay? So that's how that last one there at the bottom goes. Now, for those of you online, this review sheet's available online, okay? So these are just some example problems. You know, and I've got the wrong, this is based on my old formula sheet, so those numbers of those formulas aren't correct. So while I'm thinking about it, this first one would be number 9. Okay. And then the next one there, that's Hooke's law, is it? I think it is, so that would be 41. And then this would be 9 again, I think. And then what do we got there? We're finding epsilon z. That looks like 43 to me. And then we got delta and L, and what do we want to find there? Delta. I guess that would be 3, I guess. Yeah, 3. Okay. So it should be 9 and 41 for the top one, then 9, 43, and 3 for the bottom one. So I've asked questions like that in the past just because it takes so dang much time to run through this stuff. So rather than have you actually calculate things, I just had people fill in the formula, tell me what they would put into the formula and what they would get out. Okay. All right. So we can go over that maybe on Friday if you want to look it over this week. We could go over it on Friday. Okay.
What day was it, guys?
Monday, a week from today. So that is, I think it's the 5th for some reason.
Yeah.
Okay. Okay. So it is? Okay, good.
Would you want to do this later?
So I'll have a session for in-class students in here, and then I'll have a session in the evening for online students. Okay.
I'll do my best not to fall asleep.
Yeah, okay. Sounds good. Okay.
Pass down or face down, pass out for 20 minutes doing that.
All right, so there you go. So we'll go over this a little bit on Friday, if you like. Let's finish up torsion here. So torsion is kind of the end point of what we got here on this test. Okay, it's the last bit. No, wrong one. There we go. Let's go here. Torsion. All right, so the last thing to do here is indeterminate torsion. Okay. And again, this is like that stuff that we've done in the past with axial loads. It's the same sort of relationship, it's just for torsion instead of axial loads. So let's have a look at that. So what we're going to do here is we're going to start on the two sides, and we let's say we have two unknown reactions there. We're applying some torsion somewhere in the shaft, and we've got it attached in two different places. Let's see if we can figure out how those two torsion reactions are going to play out, okay? What they're going to be. Okay, so what's happening here, if we apply a torsion there at C, we're going to have reactive torsions at A and B, and the reactive torsions will add up to get us the torsion at C. That's the basic relationship there. Okay. All right, so the thing to realize here is what we're doing if we start with straight lines on top of the shaft from A to C and from B to C. If we apply a torsion at C and roll it over like that, C is going to move to C prime. That's where it's going to go. Okay, so there's C prime. So that line that went straight across the top will change. It'll angle down to C prime. Like that. So we're going to get a bit of twisting there in the shaft. Now, if C is anywhere except in the middle, what's going to happen here is the shears that I'm dimensioning there, they're not going to equal each other. Okay. Okay. So G times the shears won't equal. And G times shear strain is the shear stress. So most likely the shear stresses on either side of that shaft aren't going to equal each other. However, what will equal is that angle. See, we can calculate that same angle, the angle at C, from C to C prime. There's one angle there, and we can calculate it from A to C, or we can calculate it from B to C. So these angles are going to equal each other, these angles of twist. Okay. So that's what we can work with in a shaft like this. So what's going to happen here is if we apply some torsion there at C and we want to know how much torsion is being taken up by A and by B, we can get a little bit with statics. We know that two reactive torsions at the supports will, added together, will be what we apply. But that is indeterminate. There's two unknown reactions and only one equation. But we can use this angular stuff because what we know the angle is, we have an equation for that, right? It's TL over IG, okay? So we can go ahead and use this relationship as a second relationship to solve out indeterminate torsion problems. So this is just like that axial stuff where you can use PL over AE as another way to solve out a problem. This is the same sort of thing, okay? Except now we're using TL over IG. So that's how we can solve this thing out. Now this one's a little bit of an involved example here. Let's say we've got this shaft and we got two different diameters and two different lengths. We've got a little transition area at C that gets from the one diameter to the other, but we're going to ignore that transition area. Okay, we're not going to really worry about that. We're going to say that AC is 20 centimeters long and BC is 50. G, we got 10 gigapascals, and we know that we can get 70 megapascals of shear in this shaft. That's the maximum allowable shear. And if that's the case, let's figure out how much we can apply here before we hit that. Okay. So why don't we go through this one? So I know whenever I do torsion here, I'm going to need moment of inertia, and that's pi over 2r to the 4. So I went ahead and calculated that. So I got the two moments of inertia, 1.57 times 10 to the minus 8 and 25.13 times 10 to the minus 8. And the units on those are meters to the 4. Okay, so those are both moments of inertia. Okay. So that's one thing I can do right off the bat. I know I always need to do that. I also need to do unit conversions, but that probably won't be too much of a problem there. The length, I can get that into meters easy enough when I need it. G I found I in meters to the 4. So, I think I'm pretty good on units there. Now, what I know then is that angle at C can be calculated either from A to C or B to C, and that's TL over IG. And I've got the G value, I've got the I's for both sides. Now I got the lengths of both sides. So what I can do then is go ahead and relate the two torsions together by using that relationship. So I can take TL over IG for both sides. Okay. So on the left, I got TAC times its length, 0.2 meters, divided by its I value, divided by G. And on the right, I got TBC times its length of 0.5 times its divided by its I value, divided by its G. So those are two small shafts kind of combined into one shaft from A to C and B to C. So what I can do then is relate those two together because they're going to twist together. When I apply that torsion at C, they're going to twist together. And so what I can do here is I can get a relationship between the torsions. I can just work that down mathematically. The first thing I did was just crunch the numbers, and what I got there was 0.001273 TAC is 0.0001989 TBC, okay? And then if I divide by 0.001273, if I divide both sides by that number, I'll get that TAC is 0.1562 times TBC. And I could also divide through by 0.0001989, and if I do that, I'll get TBC as 6.399 TAB. So 0.1562 and 6.399 are reciprocals of each other. Okay. All right. So as long as that shaft is tied together in an assembly, I can go ahead and those relationships will hold. So TAC will always be quite a bit less than TBC. It'll be 0.1562 times TBC, and TBC will be 6.399 times TAB. All right. So we're good. Now the next thing I got to do is account for this shear, okay? I know what I can take this shear up to. I can take it up to 70 megapascals. That's as high as the shear can go. So if I can do that, I can take that shear equation and rearrange it and solve it for the torsion, okay? So that if tau is TR over I, T is tau I over R. Okay, I could do that. Like so. All right. So what I can do then is I can plug in tau max into both of these, and I can solve it for the torsion. Okay. So what's going on there? If I go all the way up to the maximum allowable shear, which is 70 megapascals, the torsion in AC will be 110. That's tau I over R. And the torsion in BC will be 880. That's tau I over R. So I'm just looking at both sides. And what I'm seeing is if I take this shear up to the maximum allowable level, what's the torsion in either side? So what I've done here is I've done two things. I've found what that maximum allowable torsion can be, and I've also figured out what the ratio between the two torsions is. So based on that, I can figure out what's going on with this shaft. See? So I can go ahead and say, okay, let's figure out which side maxes out first, okay? Because I know that TAC is 0.1562 times whatever TBC is, okay? So if TBC hits its maximum, which is 880, so if the shear in BC goes up to 70 megapascals and the torsion's at 880, those two would happen together. What's going to happen is if that happens, if that occurs, the torsion in AC will go up to 137.5. But that's too big. It can't go that high. So if TAC goes all the way up to 137.5, it'll have too much shear in it, see? Because TAC max is 110. So what that means is TAC is the one that maxes out first. And then TBC is 6.399 times that. So if TAC goes to 110, which is its maximum allowable value, TBC is 6.399 times that, it's 704. Okay? So what that's getting me are what the two torsions are. And if TBC is 110, the shear on that side is 70 megapascals. And that's as high as BC can go. And when that occurs, on the other side, I got 704. Okay? So what's happening there, when I hit 110 on the left, I hit 74 on the right. And I just add the two together, and that gets me the 814, which would be applied in the middle. So the way I think about this is I think about taking like a pipe wrench and putting it at C, like a really big pipe wrench. And I'm just going to start torquing that side, okay? So I've got this really big pipe wrench here, like that. And then I just start pushing on it, okay? I just keep pushing harder and harder and harder and harder and applying more and more torque. And as I do that, eventually this side's going to hit 110. And when it does, this side's at 704. Okay? Because they move together because they're connected together at C. and they both have that angle, that common angle that creates that relationship, okay? So the angles from A to C and from B to C are the same, okay? So if I keep pushing harder and harder and torquing more and more on that side, I'm going to eventually hit 110 at A, and when I hit that, I got to stop because I've hit the maximum shear. When I do that, I've got the shear on the AC side is up to 70 megapascals, so I got to stop. And when that side's at 110, the other side's at 704. And so those reactions are 110 and 704. So what I'm applying here at C is 814. It's the sum of the two. Okay? So that's just 110 plus 704. So that's 814 in the middle. Okay? So when I hit a torque of 814 at C, I got to stop because I've maxed out AC. BC isn't maxed out yet, but it doesn't matter because I've already maxed out AC. That's the idea. Y'all okay with that? Okay. All right, so that's just some more applications of torsion. So we went through the biaxial stuff, and then we did a little bit on power, and then we did this indeterminate stuff, okay? Why don't we get you to do one or two little things here? Let's see, we got a little bit of time. So are there any questions on any of that? You doing all right?
I got a question on the test.
Yeah.
Are you going to be switching back and forth between degrees and radians, or we never actually use radians?
I would set my calculator up in degree mode, and if you know, because yeah, you don't want to get into radian mode for all that biaxial stuff.
We never actually use the angle of radians.
Right? Yeah, you're right. We plug it in, but we don't do much with it. We just plug it into a formula.
Yeah, whenever you're calculating.
Yeah.
We plug it in, but we never use it. We never plug it into the calculator.
Yeah, so get your calculator into degree mode is what I do for this. Let's see.
No, I knew. No, you should be in degrees.
Yeah, just do the sine of 30. And that ought to be 0.5. So be sure.
Oh, yeah, you write that on the test, man.
Yeah, I do, because I've had people get that crossed.
Just to make sure you're in the right.
Yeah, because it's a mess if you
Oh, yeah.
just turns and it's a mess. All right, why don't we see if we can do a couple reactions here. Remember statics and how to do that stuff. So let's see. Go back there. Here. There. You find the reactions at A and C. Just make sure we remember this stuff. Y'all remember this stuff? We're gonna have force reactions there at A and C because those are pin joints. Yeah, it's been a while. We got X reactions too, but we're not gonna worry about them because there's no applied X forces to cause X reactions. So we'll assume they zero out. And then what do? You take the moment around one of the unknowns to solve for the other, because you got two Y unknowns. Take the moment around one of the unknowns. That allows you to solve for the other. If you got questions, you'll let me know, because this is something, I know you haven't had it for a while. We're going to use this a bit. Because we're going to do some shear in a moment. This is in your book, too. I've got these things in there. There are a couple pages up ahead. I'm just giving ahead a bit. They're on some page somewhere. Around 760 to get rid of. $760. That's where the picture's at, yeah. Okay. So if I were doing this, I'd probably start with a sum of moments about A. That's probably what I'd do. Okay, remember clockwise negative, counterclockwise positive is normally the assumptions on that. So in statics, everything equals 0. So that's how I'd start that thing off. I think you ought to be getting to 1500 or so for C. 150. Yeah. You all remember this stuff? So you can't do sum of FY off the bat because you got two unknowns. It won't get you much. You get into multiple equations and multiple unknowns if you go sum of FY. So I'd start with a sum of moment about A. Set that equal to 0. And then after I'd done that, then I'd do a sum of Fy and set that equal to 0. That's how I'd approach this thing. And we're going to need to know this stuff for doing our shear and moment diagrams and our beam stress analysis and our shear and all that stuff. So there's the two equations I'd apply, and that's the order that I'd apply them in. And here's the answers I'd be getting.
That's negative. Yeah.
Y'all remember this stuff? Something like that. So 2000 by 6, that's negative because it's clockwise, plus 8RC. RC is 1500.
They should be negative though, right?
Which?
Yeah, should be negative.
No, they're positive. They're going up.
They're
supporting means it's an equilibrium.
Yeah.
Right, okay, so that was the first thing.
Yeah, I mean, what you put into the equations, it signifies what direction stuff acts. The signs on your answers indicates whether your assumption was correct or not. So I assumed RC was up. So that would create a counterclockwise moment, which is positive. So that's why that's plus 8 RC. Then my answer came out positive, indicating that I made the right assumption. It is up. Okay. You all right with that? Okay. One more. How about that one? Remember this stuff? I want you to, okay? And I think you do too.
Really, just stay with the last one.
Oh, just stick. You're good with that? Okay. All right. Good. All right. Yeah, I know. Yeah. It's like Alien. It just keeps coming back. Right? So take that 5 kilonewtons per meter and turn it into a point load. Okay. So you're going to need to figure out how much that load is and where it's applied. Okay, then you'll take moments about A. So this is a lot like the other one. It's just you got a step to do before you get back to the other one, okay? Now the answer to that's in the units. You got 5 kilonewtons per meter. That means every meter's got 5 kilonewtons. And that acts over a 4-meter span. Okay. So 5 kilonewtons per meter over 4 meters of length. That'll get you that force, okay? Just turn it into a load and then get that distance that it is. Okay. And this is on 760, the picture is. Okay. So y'all got 20 kilonewtons for that? Because it's 5 kilonewtons per meter and there's 4 meters. So that gets you 20 kilonewtons. Yeah. Let's do Monday. We'll go over it. Okay. This is just for the test, okay? I won't give you any more for Monday anyway.
All those questions are due Monday?
Yeah, because they all relate to the test, so we'll go over them pretty well, okay? Now, y'all getting 20 kilonewtons there?
Yeah.
How far over?
2 meters.
Yeah, okay. Sounds like maybe you're remembering this stuff. And then you can go ahead and run those numbers there. So I'm getting 8 at D and 16 at A.
Yeah.
8 at D and 16 at A. So there you go. 281, 282, 302, 303, 311, and 312.
What about the, is that Torsion one? Or the next one?
No, that's called a couple there. We'll go over that next time. It's called a couple. It's
Okay.
a little different than torsion, I guess. It might be.
Well, right, that's just 2 going in the.
Yeah, right. It's a pure
I've just
moment.
never seen it illustrated that way.
Oh,
I
yeah?
always saw 2 arrows.
Oh, okay. It's just like 2 arrows. Yeah.
I guess I had 281 and 282 written down for the due Wednesday, so are they just gonna be due next week?
Oh. Did I write them? Did I make? I don't know if I did.
Yeah,
Yeah.
2 originally due on this Wednesday.
Oh, we did?
281, 282.
Yeah, I'll just push them back to Monday then.
Okay.
Okay. Yeah, I'll just do that. Okay.
Give me that get go.
All right. Okay. And okay, so there's working that thing out. So you get 20 kilonewtons at 2 meters. So the moment's negative 20 by 2 minus 4 times 6 plus 8 RD. So RD is 8 up. Sum of Fy is 0. So RA is 16. All right. So we good?
Well, don't worry, you won't be doing that kind of stuff when you're, ever? Yeah, ever. In your life.
Yeah, sure.